students, welcome back to my channel. Today we are going to see how we can find out the structure of the unknown molecule with the help of infrared spectroscopy. This video is useful for MSc students, those who have already studied infrared spectroscopy and are familiar of the frequency of the vibrations. So let's start. This is the very first problem that where they have given you the molecular formula and you have to identify the structure of this compound with the help of UV and IR. UV data is given to you and IR is given to you. So first, if the molecular formula is mentioned, then the first step is always you calculate the DBE. What is that? Double bond equivalence. And it tells you about the how much unsaturation present in the unknown molecule. So you can use and learn this formula 2C plus 2 plus N minus X minus H divided by 2, where N is for nitrogen, X is for halogen. We don't put anything for oxygen. If you have in the molecular formula, just don't have to put anything for this oxygen in the formula. So if you use the above formula and put the values for carbon and hydrogen, you will get the DBE 2. It means a known molecule is having 2 unsaturation. So now you have an idea that 2 unsaturation will be present. The UV data which is given here is you can see the intensity value here 21, and if the molar absorptivity falls between 10 to 100, it means it is a forbidden transition, and for N2 pi star transition, because the two orbitals are different, so it is a N2 pi star transition that normally occurs if you have a heteroatom present with the double bond. Okay, so usually it indicates the presence of a carbonyl group. So we can assume that our unknown molecule is having carbonyl group. Now for IR spectroscopy, the bands are given here. You have to assign, and that helps you to find out the structure of the unknown molecule. So first frequency is given here 3030, which is if you get any peak above 3000 is for olefinic CH stretching. It means we have another unsaturation present in the system in the form of alkene. Okay, you have 1776 peak, which is the range for carbonyl stretching. Okay, and this carbonyl stretching we will see as it is a higher value here. So it may be 2 oxygen are there, maybe for ester. We'll see what are the factors which are increasing the carbonyl frequency here. 1163 is for C single bond O stretching, which again confirms that we have an ester group here. 1031 and 988, the characteristic peak, which tells you about the mono substituted CH banding. Okay, so the alkene which you have, it might be di-substituted, it may be tri-substituted, cis or trans or mono. So the CH banding will tell you about the type of the olefin. So you can assume that your unknown molecule may be this structure where you have mono-substituted olefin having the ester group. But if you see this structure here, the carbonyl is in conjugation with the double bond. So therefore, if you have a conjugated carbonyl group, that decreases the strength of the carbonyl bond, and therefore you cannot have this structure here because the carbonyl frequency is given here 1776. Okay, so you should be familiar of what are the factors which increases the carbonyl frequency and what are the factors which decreases the carbonyl frequency. We have already talked about the conjugation effect in the first video of IR. You can just find the link in the description box of this video. Okay, so the other possibility with the 2 unsaturation, that the oxygen is attached to the vinyl group and you have a carbonyl and then CH3. Okay, here you can see this carbonyl strength is increased because of the you can see the electron withdrawing effect of this vinyl group. Okay, so the lone pair which are present on the oxygen is involved in the okay, in the conjugation, and so it is acting as a withdrawing group, and so it increases the strength of the carbonyl, and therefore you can justify the carbonyl frequency given in the problem. Okay, so we can say that out of two structure, this structure seems to be the correct structure. Okay, the other is wrong. So in this way you can approach the structure determination of the unknown molecule with the help of the data given to you. The second problem, again the molecular formula is mentioned here, and here only the IR data is given. So let's see. First step is the same, DBE calculation. So one unsaturation is present. We'll see the IR data here, 3413. If you get any peak in this range, we can assume it might be either OH group or it may be NH group. But you can see here the two peaks are given here in this range, 3400 to 3200. That says you have a NH2 group present here, primary NH2 group. One is for asymmetrical stretching, other is for symmetrical stretching, because of the coupled vibration of the NH2. Okay, so you have a moderate peak for NH. So you can say it is NH2 group instead of OH, because OH gives you a broad peak as compared to NH peak. Then you have this range 3030 to 2899, which says that you have a aliphatic CH stretching here in this particular range. 1667 we know it is the carbonyl stretching, because of the conjugation it is decreased. Okay, so normally the carbonyl stretching is around 1715, but it is decreased to 1667. That suggests the presence of the conjugated carbonyl group. So we can assume that you have CONH2 group. Okay, and we know it is the amide carbonyl which shows you the carbonyl frequency in this range. Then you have the NH banding here, 1634. If we are talking about amide, you have a strong peak in the range of 1634 for NH banding. We also call amide 1 peak for 1667 and amide 2 peak for 1634. Then another peak is there 1460, that is for CH banding, and so we can assume that our molecule is having CONH2 functional group with one unsaturation is already justified here with carbonyl. So the probability of the structure is it may be CH3CH2 CONH2. Okay, so since the proton NMR data is not given, that gives you the 100% accurate structure of the molecule, but whatever data is given based on knowledge, you can write down all the probable structure for the given data. The next problem, again you can pause the video and solve it yourself. I hope you can now solve it. The molecular formula is given, UV data is given, IR is given here, and if you have a knowledge of frequency with respect to the vibrational bond, then you can definitely solve it. Very first step is calculation of DBE. One unsaturation is present. UV data says you have a forbidden transition, N2 pi means carbonyl is present, and if it is present, definitely you will get the peak in IR also. 2720 weak peak is the peak for CH stretching for aldehydic group. Okay, so if you have aldehyde, definitely you will get a very weak peak in this range, and you have 1738 strong peak for the aldehydic carbonyl peak. So IR also confirms the presence of aldehyde for the given molecule, and we can write down the probable structure is CH3CH2CHO. Aldehyde can come only at the end, so this is the only probable structure for the above problem. Okay, so this problem you can say we are talking about two molecules here, A and B. Molecular formulas are given. Along with the IR data, you have to find out upon hydrogenation A converts to B. So what is the possibility of the structure? So first IR data 3450, this is a range for OH. OH stretching. You have oxygen only here, no nitrogen. 3000 is for the olefinic stretching is there. Okay, 1600 is a peak for C double bond C stretching. 1430 is for CH banding. 1050 for CO stretching, C single bond O, and 900 is for the CH banding, and it suggests what type of olefin you have. It is the trans one. So if you have any peak around 900, then the molecule could be trans. So the possible structure we'll see. Let us find out the other side also. OH, aliphatic CH, then you have CH banding. C single bond O present for primary alcohol. 1050, if you have that, suggests the primary alcohol. So the possible structure is you have the olefin, one unsaturation is present, which is trans. On hydrogenation, it gives you the primary alcohol. And this is how you can prove the structure of the given molecule. So this is our next problem, where again the molecular formula is given along with the IR peak. You have to determine the structure of the given molecule. So we know the step is you calculate the DBE. Here the DBE is 6. It means we can assume that our molecule may be aromatic in nature, because we need for a molecule to be aromatic at least 4 DBE, 1 for the ring and 3 for the double bond. So if you have DBE 4 or more than that, it is a trick. You can assume that your molecule could be aromatic, as the problems will be given to you with simple molecular structure. Now we see that confirmation of the presence of aromatic group by IR 3097, which confirms the presence of CH stretching for aromatic. Okay, you have a peak in the range of 2000 to 47, which confirms the presence of nitrile group. So basically you have already proved the 6 dBe, 4 for the aromatic, and 1 triple bond carries 2 dBe. So 4 plus 2, 6 dBe we have already proved, so no more unsaturation. 1579, and this is the characteristic peak of C double bond stretching for aromatic compound. So based on this assumption, we can find out the probable structure of the molecule is C6H5CH2 CN. CN can come only on terminal part, and so we can write this is the probable structure of the given molecule. Now this problem, you can see the molecular formula is given along with the UV and IR data. So we'll see the DBE, which is saying it is 2. UV data is given 214 nanometer. So basically they have given this data for pi to pi star transition, and basically this particular value we get it for either acyclic diene, or it may be the heteroannular diene. Since the molecular formula C4H6, we can assume it can be acyclic diene. Okay, so this is a very big clue for the given molecule. Then comes the IR data 3012. Again, it suggests the presence of olefin, and 1839 is a peak which is given for the overtone. Overtone normally are the characteristic of olefin or aromatic compound. So you are getting here 1839 overtone of 922. 16.1 is a peak for C double bond C stretching. So these two peak 3012, 1601, and along with the overtone peak confirms the presence of olefin here. And then you have peak 1040 and 922, which suggests it is a mono-substituted CH. So we can assume based on the above data, the structure could be 1,3-butadiene. Okay, so in this particular structure you can prove the TBE2, and along with the UV data also confirms this is 214 nanometer. So this is how, with the help of UV and IR data and along with the TBE formula, you can find out the structure of the unknown molecule, and hopefully you will learn this technique and can use it to solve many more problems. All the best. See you in the next video.